All right, hello. Section 2.2 on set operations. So we've looked at some notation and some basic ideas about sets, but now we're going to look at some operations, some things that you perform on a set when you or on two sets. Okay, so the union of the sets A and B, denoted by A, and then you have the symbol that looks like a U, so that is easy to understand. A union B is the set that contains those elements that are either in A or in B or in both. So this is basically the OR situation. It's either in A or in its B or it's in B or in both. Now in set builder notation, we would write it as A union B equals the set of all x's such that x is an element of A or x is an element of B. Okay, so that of course, the upside down V means or, and so we can use that symbolism. All right. So here's an example. The union of the set with the number symbol, the pound sign, the exclamation point, the ampersand that's called, and the at symbol. The union of that set with the set with the ampersand and the at symbol and the question mark is the set with all of them. So basically the union is a collection of all of the elements that you find in either of the two sets, all lumped together into one union set. All right, the union of two things. All right, so if I said the set of people that like pizza or have glasses, well, that would be the union of all the people who like pizza or have glasses, or perhaps both of those. But that would be, they both like pizza and have glasses. So united all of those people into one set. Now, in this picture here, you have a Venn diagram that shows set A is this set with the number symbol and the exclamation point and the ampersand and the at symbol. So that's set A. And set B is this set with the ampersand and the at symbol and the question mark. And of course, you see that if I combine them into the region where it's all combined into one set A and B, it's all the parts that are shaded, either the light shading or the darker shading, either one. That's the union. So the union is combining it into one larger set that includes every item. Now the intersection of two sets, denoted by A and then the upside down U, B, so A intersection B, is the set containing those elements in both A and B. Or in symbols, A intersect B is the set of all x such that x is the element of A and x is an element of B. All right? So here's an example. The intersection of this set, you guys might think of it as the hashtag symbol, but it's really the number symbol or the pound sign, and then the exclamation point, ampersand, and at symbol. If I take that set and I intersect it with the ampersand, at symbol, and the question mark, we get just the elements, the ampersand, and the at. Because intersection, you have to look for elements that are in both of the sets. And the only two elements that are in both sets are the ampersand and the at. So the intersection is just the region in the middle in the case of a Venn diagram. So if you have a Venn diagram and you have set A and set B, the intersection is not the whole thing like the union was, but it's just the the items that are in both sets at the same time. So in this football shaped region in between. All right. So let's look now at disjoint sets and the difference of sets. Sets are called disjoint if their intersection is the empty set. So sets A, which is 1, 3, 5, and 7, and set B, which is 0, 2, 4, and 6, they have no elements in common. So the intersection of the two is the empty set because there's no elements that are in both sets at the same time. Okay? And that we say that the intersection of A and B is the empty set, nothing. All right? In the case of the difference of two sets, we denote that by A minus B. It's the set containing those elements that are in A but not in B. Okay? So you look for the elements that are in A, but then you take away the ones that are in B also. All right? So in symbols, A minus B equals the set of all X such that X is an element of A and X is not an element of B. All right, so that's how to write it in set builder notation. So let's look at an example of that. So the difference of 7, 8, and 9 and 7, 9 is just the number 8. Because if we take the set 7, 8, 9 and we subtract 7 and 9, so I take away the 7 and the 9 and I have just the 8. So if I did this minus this set, it's just 8. Since 8 is in the first, but it's not in the second set. However, notice that the difference of 7, 9, and 7, 8, 9 is the empty set. Because if you have the set 7, 9, and you take away from that the set 7, 8, 9, you're taking away the 7 and the 9, so you end up with nothing. You end up with the empty set. So that's because since there's nothing in the first set that is not in the second set. All right? So let's look at another situation. Or let's look at the Venn diagrams for the difference. So if I was to look at if you're looking at this Venn diagram right here, you see I've got the universal set on the outside, the rectangle, and I've got the set A here. And if I subtract set B, that means I'm going to take away everything that's in B. So that leaves basically just this region here that is shaded white. So this is A minus B. All right? Okay, now the complement of set A, denoted by A with a bar over top it, all right, is the set of the union, or the universal set minus set A. So in other words, the complement of set A is this white region, shaded white, on the outside of set A. So it's all the elements in the universe minus set A. So it's really everything outside of A. All right. In symbols, we could write A equals the set of all X such that X is an element of the universe and X is not equal to A. The set of all X that's an element of the universe, but which is not an element of A. All right? So if U equals the positive integers would start at 1, so 1, 2, 3, all the way at forever, and A is the odd numbers, then the complement of A would be the even numbers, okay? Because what is the set of numbers that are not odd? They are even, okay? Now, here are some more examples of differences or complements. So if U equals months of the year, so of course January all the way to December, and A represents months that end in the letter R, and B represents months that start with the letter J, then find the following: A minus B, okay, and then also find the complement of B. Now, in the solution, first of all, I would specify the sets. Set A is all the months that start or that end with the letter R. So those are September, October, November, and December. Now, set B is all the months that start with the letter J. So that's January, June, and July. Okay? So once you figure that out, then you would try to do the other, do the questions. So A minus B means we're going to take the elements in A and subtract the elements in B. All right? So since there are no elements of A that are also in B, so when I do A minus B, I really get the same as set A. A minus B is just A in this case because there's no elements in B that are also in A. So it's just the set A, which is September, October, November, and December. In the case of the complement of B, that's that B with a bar over top it, the complement of B, that's the universal set, so all the months, minus the months that are in set B, the ones that start with a J. So we're going to take all the months and take away the months that start with a J. So that would leave February, March, April, May, August, September, October, November, and December. So some of the homework problems will ask you to prove or show that one set is a subset of another set. Or in the second example here, prove that the intersection of A and the complement is the empty set. So here is how you could go about doing these types of proofs or showing problems. So we go back to the definition of the things. So A minus B, what does that mean? Well, that means that A minus B is all the elements that are in A but that are not in B. So we know that X, an element of A minus B, is the same as the set of all x's such that x is an element of A and is not an element of B. So it's got to be both in A but not in B. All right. Well, if it's in A, then we know, and not in B, then it's also in A. We know it's got to be in A and this is a logical simplification. This is a rule of inference that says if we have an and, we can just remove part of it and still have a true statement because both are true, so we know that one separately is true. That's called simplification. But if we have x as an element of A, we can add to it something as long as we use an or. Now, x is an element of A or x is an element of B is implied if you know x is an element of A. But what is this set x is an element of A or x is an element of B? Well, that's basically the union that we're trying to prove over here. A union would be is really the set of all x such that x is an element of A or it's an element of B. Thus, A minus B is a subset of A union B. All right. So then let's say we want to prove A intersect the complement of A equals the empty set. So X being an element of that intersection means that X is an element of A and X is an element of the complement of A. Okay? But what does this mean that X is an element of A and X is an element of complement of A? Now, the complement of A really is this universal set minus set A. That's what the complement is. The universe minus set A. So everything outside of A. And so that is equivalent with X is an element of A and X is an element of universal minus A. But that implies that you must have X not equal to A because it's everything outside of A. So that if I, intersect the two, I've got X is an intersection, X is an element of A and X is not an element of A. Well, that's impossible. X has to either be an element of A or X is not an element of A. So we say that whole thing is false. So in other words, there's no elements that are both in A and not in A. So therefore, A intersect the complement of A really means the empty set. All right. So there's a couple questions on the homework where they want you to draw a Venn diagram. Okay. And it has multiple sets. It has 3 sets, not just 2. So how would we diagram a set such as this? A union with B intersected with set C. All right. How do we do that? Well, first of all, we draw our universal set, which is this big rectangle. And then we draw 3 sets, a set A, a set B, and a set C. And try to make them overlapping because you're going to need to shade the regions and you want to be able to, where the 2 intersect, show that in the diagram or where any 2 of the 3 intersect, okay? I need to get the marking tool, but first of all, this A union with B, how would we interpret that? Well, A union B means all the elements that are in either A or in B. Okay, so that's what we're going to do. We're going to do A or in B, and then we're going to intersect it with C. So it has to and also be in set C. Okay, so I'm now drawing A or B, which is everything in A combined with everything in B. So I'm going to start adding some things from B also. Sorry, it's kind of hard to draw with a mouse. Okay, so right there, that is the A or B part of this compound set operations problem. But now we have to do blue. In blue, do set C. So I'm going to kind of cross or do the lines going a different direction. So this is set C. And so what is our solution to this? Well, the solution to this is all the region that is shaded both red and blue, because it says and blue. So it's in red and blue at the same time. So that's all of this. So if I was to, let's say, make the solution in yellow, this would be the solution area. It's all of this. Okay, so that is your solution for this problem. A union B and then intersected with C. So you should be able to draw that kind of a or indicate where the intersection is by some other shading way. And all right, now some other items. Table 1 on page 130 in the textbook, it gives several set identities. Identities are things that are always true. So they're basically axioms or facts that you can use. But you should be able to understand these and use these. Proofs of items from these tables are shown in some formal ways, such as in the text, or informally will be done as homework problems by students. So you can see that some of them should seem kind of obvious. If you take A and you intersect it with the whole universe, that's no different than just set A. Or if you take A and unite it with the empty set, well, the empty set has nothing in it, so you haven't added anything to A, so it's still A. This next one, A union with the universe, well, that would be the whole universe. Or A intersected with the empty set would be nothing, because there's nothing in the empty set, so the set of things that are both in A and in the empty set would be empty. So you can read through these laws and think about why they would be true. This next one, the complement of the complement, is just that original set. A union with B is the same as B union with A, commutative property. A intersection of B is the same as B intersected with A. And then you have the associative laws, you have distributive laws, De Morgan's laws. We've talked about that. The complement of the intersection is the same as the union of the complements. So the complement is comparable to putting a negation on the logic statement. Remember, we were looking at De Morgan's laws when we had negations? Well, that's what the complement is similar to in terms of union and intersection and sets. And then you have the absorption laws and the complement laws. Think about those, but we need to move on. All right, then one last thing. You might have the union or the intersection of many sets, not just two, but 3 or 4 or many. So what does this mean? Well, the union of a collection of sets is the set that contains those elements that are members of at least one set in the whole collection. So we use this notation, A1 union with A2, union with A3, all the way to union with A sub n, is denoted like this, but it basically means that it's any element that's in any of those sets. Intersection, though, has to be in all of the sets. So to be in the intersection of all of those, it has to be found in every single set. All right, so that element would have to be found in every single set. All right, so I hope that this helped you to understand these various operations with sets. Try the homework. Let me know if you have any questions.